Oh, all right. Okay, everyone, let's go ahead and get started. So, yeah, welcome everyone. Week 4. And again, just as always, before we begin, any questions, anything we want to discuss before we get into it? All right. Oh, question. Yeah.
Yeah, I think on Monday you had mentioned that you might bring back the policy that if you submit one question early, you'll get some like.
Oh, yeah. Oh, I'm so sorry. You know what? I wasn't feeling well, and so I didn't think of it again. Right. Well, we were thinking of having that early deadline be today, but that seems maybe a little unreasonable. How about tomorrow? Does that work for you guys? Is that cool? Tomorrow is like the early deadline to get a token.
For the first question? Both of them.
I guess yeah, for the first question. Yeah. Is that cool? Actually, I forgot. How many parts does the first question have? 3. So maybe not even the whole first question, right? Well, you know what? I will leave it to our the whole first question.
Don't be mean.
Okay, hold on. Can you remind me what?
So 1A
Yeah.
One is showing that it satisfies
prove that the pumping lemma
All right.
satisfied.
Two is proving the generalized pumping lemma. And third is using generalized pumping lemma to show.
So maybe just 1 and 2 then, right?
Yeah, 1A
Like
and
like
1B.
1A and 1B. That's the general. Okay, guys. All right. We huddled. We have our decision. 1A and 1B. Okay. 1A and 1B tomorrow on midnight. Okay. Is the early submission deadline, and you know this is the advantage of coming to class or looking at the at the recording if there's going to be one. If you come to class and you get these opportunities for extra credit by turning your homework in early, which is great. That sound fair to everyone? Yeah? People are on board with this? All right, very good. And we'll try to remember this more systematically from now on. But we absolutely want to, I really think so much of life is understanding one's own limitations, right? And then like engineering around them, right? So I want to help you, because I was the same way when I was an undergrad. I also used to postpone things, and like it just helps, right? When there's like an external reward to help you establish these good habits. I guess many of you are seniors, but it's still good. It's still good, like never too late. Never, ever too late. All right, any other questions before we get back into it? All right, I hear some talking, so maybe there's some questions? Questions? Thoughts? No?
Are you feeling better?
I am feeling better. I'm keeping my fingers crossed, but yes, I am feeling better. Hopefully I will be fine. Thank you for asking. All right. No other questions? Then let's get back into it. All right? So, last time we were all together, you guys came up with some great ideas, like really, really, really cool ideas about analyzing this stack automaton, this PDA that we had developed for the L equals language, right? So we had our L equals, which was strings with an equal number of zeros and ones. Right? And you had that cool PDA that you made for it. We had come up with some like simple rules, like we can always have a special start state and then an epsilon push funny symbol thing, right? And then whenever we had like a state that we wanted to be accepting, we can just have well, first of all, whenever we have a state that we want to be accepting, we can just pop anything, let's say, alpha that's in gamma minus funny symbol, right? And then you can have like a self loop that again is epsilon pop alpha from the same set, right? And then finally epsilon pop funny symbol to our like actual accepting state, right? And by putting these into our PDA, and let's assume, what this tells us that without loss of generality, we can assume that whatever PDA we ever come up with will always accept when the stack is empty, right? And in fact, it'll accept if and only if the stack is empty. You guys all agree with that, right? Yeah, and then you guys started analyzing the machine, and you came up with a lot of really nice ideas, right? Really beautiful observations. We made this like stack diagram, right? And one thing that you guys realized is that if the stack ever like becomes empty again, then we can just like split the string in half at that point, right? And like recurse on each part separately. But if we don't go all the way down, right, then we know for sure that there must have been some symbol alpha that was pushed onto the stack here. And that same symbol alpha was popped off the stack here, right? Yes?
The first pop, that's supposed to be a push. First pop alpha.
No, this is, I just need to do something. Because remember another rule that we decided to make for our machines, in class especially, is that they have to either push or pop. So I just needed to do something. This really like, I wanted this to just be an epsilon transition, right? And then like have this state do all the popping. But because I wanted to make sure it was popping something, then we can do that. You know what? I'm just gonna. we anyway figured out how to do that. So let me actually just write it because I realize this is more confusing. So let me just write it as like epsilon, okay? But this is in general not allowed, okay? So when I write this, I mean like compile it the way we did it last lecture, right? So we actually push and then pop something, right? And this is in gamma minus funny symbol. Thank you for actually bringing that to my attention, that you're correct, that it did need to change. Because if I actually force it to pop, what if the stack was already empty at that point? Then we wouldn't be able to take that thing. So let's just say that just for drawing this, or is that confusing too, guys? Sorry, I don't want to like confuse you guys more. Everyone okay with this? Or does anyone feel even slightly confused? If so, please. Okay, slightly confused. All right, then I'm just going to draw it properly. Sorry, give me a second. So remember whenever we wanted like a no-op, whenever we wanted like the machine not to do anything, what we could do was have epsilon and let's say push some other funny symbol, smiley face, right? And then epsilon pop, smiley face, right? And in this way, that simulates a no-op on the stack, right? So if we do that, then we know that if we were here, we can definitely always come here, right, without messing anything in the stack. And then if we want to, we can pop all the things that are currently in the stack off the stack until finally we only have the funny symbol left to pop, right? Yes?
Will we ever cover why it's useful to do that instead of just shortening it to a no-op?
Yeah, just right now. It's just convenience, so just to be clear. It's not like, as I said, it's like just syntactic sugar, right? So it will just be convenient, right? And in fact, why was it convenient? You guys actually made this observation last time. It was because then we know when we look at the stack height diagram, it always has like 45-degree angles, right? Like there's no plateaus, there's nothing else going on. It's just all like very nice and simple, right? And that just makes our life simple. That's all. That's the only reason to do it, right? And like, again, one other thing that I hope you guys have learned is like, we want to keep life simple, right? You know, when life is simple, we're all happy, right? Like this, another hopefully like life lesson, you know, that begins Infinity 1. But yeah, you know, we want to keep life simple, right? So we know that alpha got pushed here, and that it must have gotten popped here, because this is the only time that that symbol was ever even accessible on the stack, right? Since you're only ever allowed to look at what's on the top of the stack, the first time that alpha became accessible was here, right? You guys realized that and knew that they must be like paired up like this. Like I think that was something that you mentioned there. And what I want to do right now is just generalize, right? So just as usual, something that we've done before in this class, we just want to like take an observation that you guys made, and like my contribution right now is just like pointing out that that was an important observation, okay? So that's my only like, you know, input to you guys, that that was an important observation. And now let's just try to generalize it. Let's try to think about like what would that mean in general. And you know, when we're generalizing, that means that actually the stack height diagram might have like more stuff going on before and after, but that's okay. All right. So in our actual machine, what state were we in here? This is the easiest token. Yeah. Sorry. I actually asked an even simpler question, which is, what was the state of the machine? The starting state, right? We know that in the original machine, this must have been Q0, right? You know, it transitioned to some other state at this point, right? Some state Q, let's say, right? So that's like the first observation, is that there were some states involved, right? So if we want to generalize this, then we don't want to just think only about Q0, right? So let's just restate that. And sorry, yeah, that was worth a token for getting us started, right? Let's just call this state Q, and let's call this state R, right? So, sorry, let me also just move my Q over. Okay, so we're in state Q. We took this transition. We got to state R. Is there anything else missing here? Like, what else do we need for that? Yeah. Well, alpha is the thing that we pushed onto the stack, right? Yeah. Yeah, we must have consumed some part of the input, right, to get here. So let's just call that B. Just, I don't want my A to look too much like alpha, so let's call that B. And observe that B is in the input alphabet, but it could also be epsilon, so this is no longer just the input. This is like input or epsilons on the x-axis, right? And all this means, if we write it in terms of the delta function, it says that delta of Q comma B includes push alpha and moving to state R, right? So like if we wanted to write it formally, this is just the same as saying like this is one of the allowed transitions. You guys agree with me? Right? Okay, so all we're doing is generalizing. What else should we do? There's another like thing happening here, right? So can someone help me generalize this? What should we call these things? Yeah. Okay, sure. So there's some state R2, let's say, that we start at, and then we wind up at state Q2. Okay, excellent. What else is missing here? The input symbol you consume. Do you want to give that a name? B2. Okay, sounds good, right? So then again, we know that it must be the case that delta of R2 and B2, R2, V2, okay, must include pop alpha, comma Q2, right? I'm just writing it down to remind you guys, like that's how we defined the delta function, right? And it's member of because remember it maps to a set, right? So this is just like something. Oh, I shouldn't have put the squiggles. Okay, sorry. There we go. Right? So this is basically exactly what you guys said in general form. And sorry, all of you people who contributed got tokens for that, right? And this might just seem like a little silly little observation, right? But I claim this is actually really important and really interesting, okay? So let me give some more names to things. I'm going to try to use this movable thing. And I realize that I shouldn't have put it so high up. All right, let me rewrite this. Delta. So all things QB contains push alpha R. Delta of R2 B2 contains pop alpha R2 Q2. Right? So that's the general way of writing it. So here is another observation that, again, you guys already made last time. Oh, question? Yeah.
Oh, yeah. Is the backwards E thing, is that an element of or?
That's element of.
Oh, okay.
Yeah. I'm just writing it in the other direction.
Oh.
Usually you see it in the normal way, but yeah. Yeah, and actually, okay, let me erase this for right now. That'll come later. Question?
I'm so sorry.
That's okay.
It might be weird, but wouldn't if we get a lot of ones at the end, at the beginning, wouldn't it go down like below 0 or no? Because we subtract 1 every time, right?
Okay, so this is like a stack height diagram, right? So the stack can never be negative, right? Like the stack can only build up. I think maybe you're thinking about the number of zeros minus the number of ones. Right. So what we're trying to do right now is we're taking the lessons that we learned from that specific analysis, which is done. You know, we don't have to revisit it. That's done. We already proved everything we needed to prove last time about that, right? And now we're trying to take the lessons from it and like generalize to see what does it tell us about a general PDA, a general stack machine, right? So that's what we're doing right now. And I initially drew this as this is the very beginning of the input, but the reason I drew it this way is just to say like it could be somewhere in the middle, right? So I'm just to make it more general. That's all. Is that good? Okay, very good. All right, so here's the other observation that again you guys made in the specific case last time. I'm just reminding you. So let's think of all of the strings, right, that could ever get you from R to R2 with like the stack level, okay? So let me call that maybe S R to R2, okay? So again, we'll define that to be all strings, all input strings, that cause the PDA to transition from state R, with empty stack to state R2 with empty stack. Okay, does that make sense? So all the strings that could move us from R to R2, like keeping the level straight, right? And note that I wrote empty stack because from the point of view of this machine that's going from R to R2, there is nothing below here, right? Because it never ever pops below that, right? It never actually, and we don't want it to, right? Because if it pops something below that, then it might have pushed something different from alpha here, right? You guys agree? Okay, that was the observation, again, that you guys made last time. I'm just writing it in a little more general form here, okay? And of course, there is, so far we've defined S. There's a set of strings that take us from R to R2, right? And we can similarly define S from Q to Q2, which is from here to here, right? So here's my question to you guys. And again, you guys already figured this out last 2 days ago, right? But from the diagram, from what we've already seen, what must we know about how this set relates to this set? Do I see little hands? Yeah?
We know
Sorry.
that SR to R2 is a subset of SQ2.
Okay. I like where you're going with it. Okay. So you're saying, well, SR to R2 is kind of like inside of this diagram, right? But that's not exactly a subset, right? Because after all, there are these like additional letters that pop up here, right? So you're on the right track, but not quite there. But I see some, wheels turning. Yeah? Do you want to?
Substrings of the strings while the input in SQ2, SQ2.
Excellent. Right. So starting from what you said, which is definitely worth a token, you're extending it a little bit to say, like, actually what he meant to say was it is a set of substrings, right? And that definitely does seem to be the case, right? Because there is this option, because we know that these two transitions exist, right? We know that there's an option to get to here, right? Okay, excellent. We're getting closer, What specific substrings? Yeah.
SR to R2 is SQ to Q2 substrings with the first and last character.
Exactly, right? So what she's saying is that, what did I do? Oh, there. I should never do that. Okay, right? Excellent. So you like brought us home, right? And you said, indeed, there must be a subset of strings, right? And what is that subset? Well, it starts with B, right? Because of this transition that we could take. And then the little circle is just concatenation, just to make it more clear. Then we can have SR to R2, right? Because any string that takes us from R to R2 without disturbing the stack is completely valid here, right? And then finally at the end, we just need to put B2, right? And that'll get us all the way back to Q2, right? So awesome, congratulations. That was definitely worth a token, right? And this is, again, it's really the same things that was driving your investigation last time. And now we're just generalizing and kind of writing it down as a statement. Does this make sense? Any questions about this? This is probably the most important observation. Yeah?
Do you have to specify what B and B2 are? Because you can't just plug in any character, right?
Absolutely. So they are exactly these ones, right? And I like your question, right? So really, this is true for all states Q, R, R2, Q2, right? For all B and B2 in sigma epsilon, right? And for all alpha in gamma, right? Such that these two conditions hold, right? If these two conditions hold, then we know that this statement must be true, right? So you're absolutely right. We should specify it, right? So thank you. That's also worth a token, right? So like, what we're saying is that whenever this pattern happens in the PDA, right? Whenever we have these like pair of transitions where one pushes alpha and the other pops alpha, then this is always true, right? Question or thought? No? Just a hand movement. All right, that's good. It's all good. Excellent. So this is something that's always true, right? Whenever anything like this happens. What else is like this that like corresponds to the main observations that you guys made last time? Like what other statements like this can we say? Is that an actual hand this time? No? Yeah. Yeah, exactly, like corresponding to the inductive proof from last time, right? So yeah, so this was one of the main steps of the inductive proof from last time. What was the other main step? Yeah, I see the hand movements, right? The other main step was this, the decomposition, right? So can you guys help me with that? What would the decomposition rule look like of this type? Yeah? Yep. Let's call this Q3. Good. Excellent. Just a little bit slower. So Q to Q2, right? Concat S Q2 to Q3, right? That is always true, right? This is in fact true for all states Q, Q2, Q3, right? And in this case, we don't even need any conditions. It's just always true, right? Excellent. Very, very good. So we get this other condition, right? Definitely worth a token. Thank you. And then, finally, the only silly little piece that's missing, okay, is what do we do at the very top? What's the most trivial case of our base here? Yeah. Yeah. So how can we write that here? So like, yeah. What should I say? It's just what? Sorry, I could use. Well, what would the subscript of the S be, right? Like from what state to what state? To itself, right? So it's just like Q to Q. So for all states Q, right? Q to Q just contains the empty string, right? That's it. You guys agree? And actually, that was and thank you. That's definitely worth a token, right? This like trivial base case, but like this is the one that you can't possibly disagree with, right? Like the empty string definitely takes us from a state to itself, without disturbing the stack, right? Obviously, we just stay there. We don't do anything, right? Yeah. Can you say it a little bit louder? Absolutely. This is like not even doing a single transition. This is us just staying at Q and like not doing anything, right? It's just the base case of like the induction, where we're saying that let me give you. I'll get to you in just a second. Like this is kind of the following. Suppose I had this like DFA, right? This obviously does accept epsilon. Why? Because we get there and we don't do anything. We don't even take a single transition, right? So that's all this is saying. Like if you just don't take any transitions, that's the same as just taking the empty string, right? Any questions about this? Question? Yeah?
I think I understand this. I just don't
Okay.
understand why you said that it happens at the top.
Oh, right. So I think we had just sort of run out of time, maybe, or maybe I wasn't feeling well. One of those two things happened at the end of last lecture. But we talked about us basically doing like an induction, right? And if you think about it, the way that induction worked was by like raising the land, right? Like let's say we want to focus on this string, right? Then we would be like, okay, we never touch sea level, right? So we take a look at these two transitions, and then we like raise the floodwaters up to this level, right? And then we're like, okay, now we can just break them apart, and we just keep doing that, right? Yeah, let's say it's that.
So now the top is at the sea level, so it's
Exactly. Yep. And at the very top, it's just the base case of an epsilon, right? That's what we did last time. So the same thing we can do again this time, right? And that was it. That was literally all we did last time, right? And that is actually everything that can ever happen in any PDA. Every PDA is governed by these rules, right? And then let me ask you this. What is the final set of strings that our PDA will actually accept? And I want to remind you guys now of what I erased. Oh, hold on. Where did I put it? Here I put it, yeah. So without loss of generality, we can assume that we have a special start state. Let's call this Q0. And we have exactly one accepting state, which only we get to when the stack is empty. Let's call that QF. Right? So what is, so if I have some PDA, so I'll write it this way. I have, or let's say for all PDA M equals, stuff, right? The language of M equals S of what, is what I'm asking you. Yeah.
It goes from Q0 to QF.
Exactly, right? Like the only way our PDA is going to accept anything is if it takes us from the starting state to the unique accepting state without disturbing the stack, right? It starts with an empty stack and it ends with an empty stack, right? And it's just if and only if, right? Okay. And that's it. These are the rules, right? So from every PDA that we start with, excuse me, if we just use the rules of our PDA to build up these sets of strings, we eventually wind up with the entire language of the PDA, right? And you guys actually essentially figured this out last time, and today all we did was just generalize it, right? To make it work for everything. Yes? Yeah.
When you define the first rule there, where it says for all states,
Mm-hmm.
and all B's and all alphas,
Right.
if the input string is 0, 0, 1, 1, for example,
Mm-hmm.
then by that definition, can't you pair the first 0 and the first 1, but they're not on the same level?
Right. So good. Right. What you're saying is that you're kind of worried about this. Sorry, that's too low. All right, over here. So you're kind of worried about this input string, right? And you're saying, wait a second, I can push a 0 when I see the first 0 from our machine from last time. And I could pop that 0 actually here, right? So does that potentially create a problem? Well, let's think about it, right? So if we try to do that, the only string we have left inside is 0, right? But is 0 ever going to take us from any state to any other state without disturbing the stack? It will never do that, right?
I'm just saying it's like
Yeah.
by the definition here. Is it
Yeah.
like as long as those two transitions exist, we're
Yeah.
transitioning from the same thing?
Yes.
So is it like only if
No. I literally mean that, right? And I'm trying to argue why this wouldn't be a problem by pointing out that the only way this would be a problem is if, like, we were just focusing on this substring, right? And we were trying to say, okay, I'll take this push, take this pop, apply this rule. B in this case will equal 0. B2 will equal 1, right? And the only thing that's left on the inside is just 0, right? But now the point is that 0 is not in SR to R2 for any two states R and R2. So this will actually never get created. And as a result, we'll never create this either, right? So it's like you have to think about it from that perspective, that first we build the inside, and then we build the outside, right? Just like how we did it inductively in the proof. So like we start from the peaks, right? We put like an epsilon here, and we build it, build this, concatenate it, build it, concatenate it, and that's how we finally get our string, right? That was actually a great question. Yeah, thank you very much for it. Worth a token, actually. Yeah, yes.
Just to clarify, right now when we talk about Q and R in our statement, we are actually referring to the combination of your current state, your machine, and the stack, right?
No, absolutely not. Sorry. Yeah. Let me no, absolutely not. We really mean states. So by states here, I can write it this way, more mathematically, just to make sure that makes sense. So we're saying for all Q, R, R2, Q2, literally in Q. So just like actual states of our PDA.
So your Q could equal to your R, even though you push something.
Yes. Okay, that's another very, very good point, right? Is that whenever we write stuff here, it is totally possible for, maybe I'll write here now. So, possible for Q to equal R equals R2 equals Q2. Like even that is possible, right? They don't have to be distinct in any way. And if we ever require things to be distinct, we always write that, right? We say for all Q are such that Q is not equal to something, right? Since we didn't write it, it literally means everything is possible. We can have repeats everywhere. And that is really what happened last time, right? Like there was our one main state, which had like all these loops, right? So in fact, in almost all of the examples from last time, they would have all been the same, right? Q would have equaled R equal R2 equal Q2, right? Yes?
Another quick clarification. I know this is how we're talking about it, but are all PDAs defined to only accept when the stack is empty, or is that just like how we're going with it?
We're going with it exactly because it lets us do this, right? And remember, it's just, if you don't like it, just don't do this,
But
right?
so it's not like a formal.
It's not a formal requirement for a PDA, right? We didn't define it that way. But by adding this and this, we know that it's without loss of generality, right? So without loss of generality, we can just assume, and I highly encourage all of you to always do that. Whenever you're thinking about PDAs, always write without loss of generality. The PDA only accepts if and only if the stack is empty, right? Yes?
sorry, just another clarification. When it says transition from state R with empty stack, does that mean like the stack? What does that mean about the stack?
Yeah. Good. Another way of writing it is that it transitions from state R to R2 without disturbing anything that's already on the stack,
Okay.
right? Like it never pops below the current level.
It's like the shift up.
Yes,
Okay.
it's like the sea level, right? Like it never goes below sea level,
Okay.
right? As we keep raising the sea level in our proof, right? All right. Any other clarifying questions? Yes.
Just to clarify, the PDA that we define has only one unique accepting state.
That's right. Because of this transformation, we know that without loss of generality, it only has one unique accepting state.
However, there could be a PDA with more than one.
Yes, in that case, we would just do the same exact transformation to all of the original accepting states, right? If we had another one, we just add a copy of this and have it point to the same QF at the end.
I see. So we
Yeah.
designed it in a way to build.
We design it in a way to force that to be the case. Yeah, and again, I also encourage you all to do that. Like whenever you want to deal with a PDA, say without loss of generality. I assume there's a unique accepting state because of what was shown in class, right? Yes?
I have a question that might be a little unrelated.
Okay.
But say our L equals is another element in our alphabet. Now I have like 0, 1, and 2.
Okay.
Is it possible to have a PDA that can have equal numbers of 0, 1, and 2?
I love this question. I love this question. All right. I want you to remember your question, okay? And I promise you we will get to it, but just give me a little more time, okay? Because I want us to sort of just build some groundwork. A big part of me wants me to just be like, oh, let's think about your question. but actually, let me try to be a little more disciplined and for the sake of the class, like push us in a direction that is a little more helpful for learning, right? But awesome question. Really, really awesome question. Please ask it again at a later point, okay? All right. Any other clarifying questions about this? This all looks good, right? So let me actually take your question, right? Which is about like, wait a second, how do we build these things up, right? And expand that into another thing that we do in this class, right? So like, what do we do in this class? We think about machines and we try to like find equivalent ways of thinking about them, right? And one of the things that we did together was we did these like, remember we did these closure rules, right, for DFAs? And we used that to define regular expressions, right? Similarly, in some sense, right, it was a lot faster, but we came up with these rules, right? These kind of like things that are true. So can we do something similar? Can I take this idea, what we have on this board, and like make some kind of new but simpler looking object that's like inspired by this? Okay, that's the idea that I'm going to ask you guys to do with me. So let me scoot this over. And yeah, thank you, really. Oh man, I didn't realize we had these movable boards. This is so much. This is so convenient. I don't have to erase everything. Okay, so all right, we've got these things, and we already know that when we actually apply these rules, we apply them like inductively, right? You kind of actually start with these like base cases, right? And then we keep applying them to build something, right? So let's kind of lean into that as a way that we could start. And I want to have, let's call them replacement rules. Okay? And as one example, we could have like A goes to epsilon, right? And this just tells us, this is the analog to this like trivial rule, right? It just tells us that if I see this like capital A, and I'm going to have a distinction between capital letters and lowercase letters. A capital letter we can think of as like a variable, right? And like one option we have in front of us, so we can just replace A with epsilon, right? That corresponds to this rule that says that, hey, whenever I have an SQ to Q, I could think of it as just being epsilon, right? Like at the top of our inductions. Yeah, like at the top of our little mountains, right? Question or thought? Yeah.
Is the
Sure. Yeah, let's start with that, right? Let's get started. So, do you have a suggestion for me? Yeah. Okay. I mean, like B, right? Like lowercase b. So yeah, maybe I'll put like comments over here. So B is in sigma epsilon. Okay. And then what should come after it? Could be A again, but in general, it could be some other thing. Let's maybe call it B. Okay. V2. Yeah. Right? We can just allow rules like this. This again just exactly corresponds to, yeah, sorry, let me put a check mark here. So, okay. Great. That was a great way to get a token. All right. So, what else could we do? What else could we do to make these like replacement rules? Yeah. Sorry, what do you want me to put here? Uh-huh. Yeah, so we have A over here. Just what do you want me to write here? Capital C? Capital D? All right. Cool. Right? Yeah. Yeah, so let's just think about it this way, that here A, B, C, and D are the members of V for variables. Okay? So we're just defining a set V, which is like our variables, right? Which kind of correspond to our sets here, right? And that gives us this one. And observe this is already enough, right? Where kind of the rule is that there's going to be some special variable. Let's say that there's a special starting variable. We can call it S, which is a member of V, right? And then what we can do is we can derive a string by continuously replacing our variables with other things on the right, until we're left with only elements of sigma epsilon, right? So maybe to make this a little more intuitive, maybe let me just come up with a simple example, and then I'll let you guys come up with examples, right? So how about this? S can go to epsilon. That's one option. But S can also go to 0, S1. Okay? And that's it. Those are the only replacement rules that I allow. What does that do? Yeah?
You keep repeating this, like the second rule.
Yeah.
Just get like a ton of zeros, and then you can do 1%.
Yeah, so indeed, this yields the language. And sorry, I'm just going to call this whole thing G. And I will say L of G. In this case, you're absolutely right. It's 0 to the n, 1 to the n. Right? Our familiar is 0 to the n, 1 to the n. Right? Awesome. Definitely worth a token. And let's just think about why that's true. Right? So I could start with S, and I could just directly replace it with epsilon. That gives me epsilon. Right? I could start with S, apply the second rule, and I'm drawing it as a tree, which, if you think about it, it's going to make a lot of sense, right? And then, for example, I could apply the same rule again, and I get 0, S1 again. And then finally, I just replace the S with epsilon, right? Then this creates the sort of left to right traversal, depth first traversal of this tree. This yields 0, 0, 1, 1, right? And let me just write this also as like literally a replacement rule. I could go from S to apply the rule 0, S1, apply it again, 0, 0, S1, 1. Now apply the first one, and I get 0, 0, epsilon 1, 1, which is just literally equal to 0, 0, 1, 1, right? These are two ways of looking at the same thing, where the tree way is a lot more convenient, right, as a way for us to think about it. And this is like the set of actual replacements that happened. Oops, sorry. Uh, 0, 0, 1, 1, right? And like this became this became this, this became this, right? And remember, we only end up with a final string when all the variables have gone away, right? Again, that's like based on our our like base case, right? Eventually, we just get rid of all the variables by like replacing them with something that is only a string of like things from epsilon, from sigma epsilon. Yeah.
So for your special starting variable,
Mm-hmm.
can we only hit the variables that are directly defined with an error to a character in the alphabet?
Right. So I mean, you have to have some kind of replacement rule that involves S on the left-hand side, because otherwise you could never do anything with it, right? And it only finally makes a string when you've gotten rid of all the variables, right? Like we can't stop here. That's not allowed, because so far what we've made is 0, 0, S1, 1, but that's not a string in sigma star, right? So yeah, maybe you can make a note. Oops. This is, not a member of sigma star. This is not a member of sigma star. This is not a member of sigma star, but this is a member of sigma star, right? Which makes us happy. Yes?
Could you do something like, for that last rule, A to C or D?
Good. I'm glad you mentioned that. So observe that I can anyway have multiple rules for the same variable, right? Like in this example here, we had like 3 rules that all involve A, right? So that already gives you like choice, right? Since we're talking about stuff like that though, just like with regular expressions, we could write it as, for example, it could be like CD or AB, right? And we interpret this as just meaning the same thing, as there being one rule that goes like this and another rule that goes like this, right? Cool. All right. Any questions so far, just about how we're defining our? We're still in the process of defining it. We haven't like finished the definition yet, but hopefully it's kind of starting to make sense now. Question? Yeah.
Yeah, so does reaching epsilon in this rule like equate to reaching popping the symbol like doing a push down epsilon?
Reaching all the way to the epsilon in like this derivation is analogous to when we reach the top of the mountain, right? Because like we've already made everything here, and at the very begin, and at the very tippy top of the mountain, we're like, okay, I don't want to go any further. I just put an epsilon there to like cap it off, right? Excellent question. Okay, sorry, I actually cannot hear you, especially when I'm moving this thing.
When we're processing, like when you were showing us that like S is like not part of like the alphabet, like what happens like if we never reach a state that we actually like? Could
Yeah, right? Like whenever we convert a PDA into these replacement rules, then we are actually guaranteed to have lots and lots of rules like this, right? But if you're just making up your own replacement rules, you could actually accidentally make it so that you can never construct a string, right? In that case, we would say that the language of the grammar is just empty because it just never manages to make a single string, right? Yes?
So just to clarify for that example you gave on CD or AB,
Uh-huh.
doesn't the A to CD rule already contains the A to AB rule?
Why would it already contain it?
Because you could have a C that equals to A. C refers to any variable, right?
No, no, no. This is a specific variable. So like in this rule, okay, so for example, I mean, I gave you like a really simple example here, but like s isn't just some arbitrary variable. It is the variable s, right? So similarly here, sorry?
But your S still changes in this process.
So the s evolves,
Yeah.
but the individual s does not change. Does that make sense? Like I took s and I rewrote it as 0s1. That's the same s, but now it just has a 0 and a 1 on its side. Then I rewrote that s as 0s1. It's the same s, but now it just has zeros and ones on its side. And then we decided, you know what, now I'm going to take this rule instead. And this s becomes an epsilon, and then that's it. We don't have any variables anymore. Yeah? Okay, very good. Yes?
Couldn't we just apply the second rule forever? And we never implement it because
Absolutely. Yeah, 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 yeah. This would, in some sense, this, if we just if we just didn't have this rule, then the language of this grammar would be empty, right?
even if we have this rule, we don't have to take it.
That's also true. So there is like an infinite derivation tree, right? That would never get rid of its s, right? That derivation tree produces no strings. It's kind of like, imagine our PDA, just like pushing zeros forever, right? Yeah, that is a thing it could do. In that case, it doesn't like accept any actual string.
We only care about like real values.
We only care about like finite derivation trees, right? And this concept of a derivation tree is really important. So please also ask me if there's anything unclear about how once I have a set of replacement rules, it can give rise to a derivation tree, and then eventually the left to right depth first traversal of that tree exactly corresponds to the string that is derived via that derivation tree, right? It's a very important point. Question?
So for this G
Mm-hmm.
to like stand up or like exist, there has to be a definition so that it either becomes epsilon or a constant.
Yeah, there has to be some way to like terminate, to end it, you know, to terminate it. Yeah, absolutely. And in fact, I'm just going to use that as my excuse to say that when we're talking about replacement rules, we actually call this set the set of terminals. Okay? Because basically they terminate that part of the derivation tree, right? As soon as we get a terminal, I'm not allowed to go below. Like it can't have children, right? Only variables can have children, and they must have children, right? So in every derivation tree, terminals can't have any children. Variables must have children. They're not allowed to not have children, right? They must continue to have children until we're left with only terminals, right? So that is just the way that we define things. Yes? Okay. So okay, let me take a step back. So we've already observed that whenever we convert a PDA via this procedure into a set of replacement rules, we actually have a whole bunch of replacement rules like this, right? For every single state, we have a variable to go from that state to itself, and it always just goes to epsilon, right? So in fact, whenever we're converting from a PDA to such a thing, we always have that, okay? We haven't yet talked about going backwards, so that's something we have to think about, okay? And I'd like you guys to think about it, obviously. So at least you should feel comfortable that like at least that direction we're okay, right? Now in the other direction, you are absolutely correct. We could have a set of replacement rules that actually just never allows any strings to be created. And then yeah, we have to think about it. You know, we have to think about how would that work. You know, we haven't talked about that direction at all, right? Okay. Excellent, excellent. Things are making sense mostly. Yeah. All right. Oh yeah.
Could it be possible for a terminal to point to like an empty? Like B arrow empty?
No. Remember, terminals can never have children. So the left-hand side of every replacement rule is required to be a variable. Okay. Yeah.
I'm not so sure, like convinced that when we have a PDA, we can always end up with replacement rules. Because like what we said about all the S sets
Mm-hmm.
has to do with like the subset relation, but I'm not like certain that we are, or like that we can use that to kind of like totally cover like SQ0 to QF. You know what I mean?
Yeah. That's a great. It's just totally valid. Okay. This is probably the most complicated thing that we've covered so far, and I've kind of swept it under the rug. I want to reassure you that it is indeed true, and I'll just point again to like the main reasons why it's true, and then I will refer you to the book if you're, or actually I'd refer you to first try to prove it yourself, and then if you fail, to look at the book for some guidance. But yeah, remember every PDA has to look like this, right? There has to be like a stack height diagram that starts empty and ends empty, right? And this is the only thing that can happen, right? Like if you go up an individual mountain, it must be via this replacement rule, if we think about it as a replacement rule, right? When we get to the top of the mountain, it must be via this replacement rule, right? And on the other hand, whenever we have like two mountains at any given sea level, right, the only way we can combine those mountains is via this replacement rule. So it's just literally everything that can ever possibly happen inside of a PDA. That's the moral argument. You can actually carry out an induction and prove it, and I encourage you to do it, maybe in your free time after class. But I don't want to get more into it just because we don't have that much time. And I'm trying to keep us on schedule for not having to like change the midterm and date and stuff like that. So with that in mind, I'm going to try to be a little bit more on schedule in some way. Oh, it's still up to you guys. If you guys say, no, we demand the proof, then okay, well, well, that's what we'll do. You know, you guys are in charge. All right. So what I would suggest that we do next is let's just try to formalize this idea of replacement rules a little bit more. Does that sound good? Yeah.
Quick thing, do we ever call the variables non-terminals? Or
Yeah, we could call a variable a non-terminal. That's totally fine.
are they typically called variables in our?
They're typically called variables and terminals.
Okay.
Yeah, those are the only two kinds of symbols that exist in these replacement rules: variables and terminals. Okay. All right. And another thing that I would like encourage you guys to think about is, all right, motivated from PDAs, you guys, came up with these specific replacement rules, right? But should we limit ourselves only to those? Maybe we should be a little more general, right? So we can try to do that maybe right now. Okay? So let's try to define a notion of these like replacement rule systems. And I will actually erase this now. Yeah. I wish there was a way of like sending this backwards, because then I would, because I want to keep that up. Anyway, it's all right. Okay. So I think this is also a good time for me to just like declare the true name of these things. Yes.
So just a quick last question about that.
Yeah.
The replacement rules. So that would like A to C and D means that we could like C and D separately, right?
Yeah, this means that I am allowed in my derivation tree, right, to have like a variable A somewhere, and I can just replace it with C, D.
Yeah, and then later on we'll be able to replace C and D.
Yes, and later on we actually, in fact, must replace C and D with something else, right?
Maybe epsilon equals something more.
Yeah, maybe epsilon, maybe something more, right? Okay. All right, I hear a lot of like, okay, so maybe we shouldn't move on. Are there questions? Additional thoughts? No? Do you guys have a question? Okay. All right, so if not, then let's actually just define this a little bit more. I see a question. Sorry.
Just to like clarify for the replacement rules,
Mhm.
like in this case, could that be like a full like set of replacement rules, or would you have to define like a rule for capital B specific?
Yeah, you would. That's a good point. Like these are just the types of rules that you guys have come up with so far. But like this is so far I've only given you one example. This is one example of like a full set of replacement rules with only one variable, right? And you'll be surprised. Even just one variable, you can do a lot with, with these things. Yeah.
Another clarification.
Yeah.
For this, does that only ever work for the one length of string?
Sorry, what? What are we talking?
Um,
What are we pointing to?
Can can that tree
This
work
derivation
for
tree.
all n?
It
in
would
language?
it would be a different derivation tree for each one, right? So for example, this is the derivation tree for epsilon. This is the derivation tree for 0, 0, 1, 1. There would be another derivation tree for 0, 1, right? That would be s goes to 0, 1, and then s in the middle, and then s goes to epsilon, right? This is the derivation tree that gives you this,
Okay, so
right?
so you would just put more s's if you wanted to make it longer. In this
Yeah,
case.
yeah, exactly. I would just have a longer like chain of s's
Yes.
in the middle.
Okay.
Yeah.
That's exactly right. Yeah, yes.
So I'm assuming with a more like complex language,
Mm-hmm.
we would be able to make identical derivation trees for the same string.
That's a very actually good point. So in this example that I made here, this is called an unambiguous set of replacement rules because every single string only has one derivation tree, right? But absolutely, there can be, there definitely can be, excuse me, there definitely can be sets of replacement rules where there could be multiple derivation trees that yield the same underlying string. Okay? And in fact, if you just try to do that conversion from a PDA to a set of replacement rules, you actually would generally get a potentially ambiguous set of rules, but that's fine. Like it's not a big deal. It's just that there can be multiple derivation trees that still yield the same underlying string. When you do the left to right depth first traversal of the tree, you end up with the same string, maybe with some additional epsilons in different places, right? All right. Yes.
If we have A to epsilon and B to epsilon in one of our replacement rule sets,
Mm-hmm.
which one is the starting variable, or could we choose any?
We have to just declare one of them to be the starting variable. And as a general rule, we're just always going to call that S.
Oh, okay.
Yeah. Maybe, you know what, maybe before we go to more general things, I should just give one more example. So that's a particularly nice one. Let me give one that's a little sillier. How about this? S goes to AB. A goes to 0, A, 1. A goes to epsilon. B goes to 1, B, 0. B goes to epsilon. What do you guys think? What does that do? Yeah.
That's the language of all strings that have the equivalent number of zeros and ones.
Ooh.
Just any string of zeros and ones.
Okay, I can't resist. All right. She brought it up. We have L equals, which I erased. That's okay. All right, let's forget about this. Because you know what I mean? Like, why should I be writing stuff? You guys are supposed to come up with all the ideas, right? So let's recall L equals, right? L equals is the set of all strings, x in 0, 1, such star, such the number of zeros is equal to the number of ones, right? All right, please tell me, how should we do that? What is the set of replacement rules for this? Do you want to get us started?
Starting with S,
Okay, yeah, there we go. Good way to get it started. Excellent, yes. That definitely works. All right, so token for you, also for proposing it. What else should we add to this to get every single possible thing in the language? Now observe, one option for us would be to start with our PDA and just like convert it, but that would be kind of painful. So I want you to think about it like from scratch. You know, how are we going to do this? I see a lot of hands there, yeah. Yes?
If we have like all permutation of 0, 1, S, so it would be like S, 1, 0, 0, 1, S, and then the one from the which is 0, S, 1.
And then
1, 0, S as well.
S0, 1. Okay, and you also want the other way?
Yeah, like all the permutations of the
Okay. 1, 0, S, S0, S1, 0, like that?
Yeah.
Okay. What do you guys think? So sorry, before I take your suggestions, I want us to respond to each other, right? So token for you. What's wrong with this? Does it work or does it not work? Yeah.
It doesn't. I mean, it might, but I just feel like you could make it shorter by like doing
Okay.
S1, S0, for example, something like that.
Okay, so your objection to this, it just seems too long.
0, S1, S, for example, and then the other way around.
Okay, all right. Okay, I like that. That's a reasonable objection. Even if you don't think of something that it doesn't do, let's try to make it simpler and shorter. So you were just saying, why not just have these two like that, right? Okay.
Actually,
That.
I think I was more saying like 0S1S again, and then
Okay.
the other way around. Wouldn't you want to substitute?
Like that.
Yeah, I think so. And then also
Okay.
like an SS or something.
Okay. She also wants S goes to SS, right? This is a genius idea, right? This corresponds to, our mountains, right? This is like, look, I can, you can have mountains, but then like, you have to give me ways to attach the mountains together, right? So this is a genius idea, which is an excellent contribution, definitely worth a token. Okay. What do you guys think, actually? Can we stop first? I really want us to stop. No additional suggestions. We're not allowed to change it. If you want to simplify it, you can give me that. That's the only thing I'll allow. But does this miss anything? Can you guys think of any strings that we don't get from this? Yeah? So you just remove it, okay. Okay, so you are claiming this is sufficient, right? Excellent, I like it. And let's think about the proof, right? And the good news is you guys have already come up with all the ideas for the proof for last time, right? So we had our number of zeros minus number of ones graph, right? And we know that it can go below, but it always has 45-degree angles, right? It goes up and down. So, all right, explain to me how using these rules. Maybe do you want to just tell me with this? Just take this picture. How would you break it up? What would you do roughly? Yeah. So of course the first thing we do is apply the S goes to SS to break it up this way, right? So now we have S, one S for that, one S for this. Okay. Let's say this side. What do we do here? Yep, exactly, right? We know that this first one must be a 0 because the number of zeros went up. This one has to be a 1 because it went down, right? So now we use the 0 S1, and we again have the smaller case, right? Then we again break it up, S goes to SS, and similar and so on and so on, right? And then we use the epsilons to get the peaks. And we do the same thing in the other direction to get this, right? So that'll always work. This is actually a minimal set, and that works. And yeah, thank you. Both of you guys get tokens for sure, right? So here is another example of a set of replacement rules. Interestingly enough, we again only used one variable, S. We didn't have any other variables. But you'll see that that's very often the case. It's very often the case that we don't really need additional variables. Yeah?
Wait, I'm just kind of confused on why we have S to SS. It just makes it easier for us to think about it.
Yeah, absolutely. We absolutely need it, for example, in this proof, right? Every time we cross the x-axis, that is corresponding to us using an S goes to SS, right? And then we raise the sea level again, and then again touch the x-axis. We again use S goes to SS. And then for each of the individual mountains, we can just use either 0 S1 or 1 S0, right? To go either down or up the mountains, right? So S goes to SS is actually pulling a lot of weight, right? It's doing a lot of work for us. Does that make sense? Kinda, okay, yeah.
Try and make the string 0, 1, 1, 0 without it. Because I have the same thing, then I was thinking about it, and I was like, wait. Because this says that it either has to start with a 0 and end with a 1, or start with a 1 and end with a 0 without the SS.
Right.
Does that make sense?
Yeah, that's a great example. Thank you for bringing that up. Also worth a token, right? This is such a natural thing for us to break in the middle, right? And then you've got your two S's there, right? Excellent. Excellent. Very, very good. Okay. So, yeah. So let's try to define this a little bit more generally. Okay. And I'm just going to give you the name. Okay. So this is the historical name for these kinds of replacement rules. They are called context-free grammars. Or CFGs. Okay. For those of you who are in linguistics, you probably have heard of these things before. But they're actually very important. They're something that are very important historically. And as the name implies, they actually do come from linguistics. This is actually an idea that originates in very, very simple models of the English language or of other of other human languages. But as we'll see, it's really a computer science idea. All right, and you guys are going to define it. You already defined it there, and now we're going to define it properly. So a CFG, right, is some set of things. So please tell me, what should it be? What do we need to define a CFG? Yeah.
Do we need like a starting state, a starting variable that exists inside of it?
Good. So maybe first we need the set of variables, right? And then we need, so I'll just write it this way. V is the set of variables. And then what you're saying is I need a special starting variable, right? Which is the starting one. Okay, that's what we've got so far. Thank you, definitely worth a token. Yeah? Yeah, we definitely need a set of rules, right? So we need R to be our set of rules. Now, how should we define that? Like what exact, this is really the crux of the issue, right? Like how do we define a set of rules? We have a lot of options here. I'd like you guys to think about some of them. And the way we define this is really going to be how we generalize what's over there, right? So, okay, you got it started. That's worth a token. What do you guys suggest? I see a few different hands in the air in the back. Yeah.
A variable to a variable or a
Okay, so you want to define it potentially as a function, right? So R will be a function that maps the set of variables to what?
set of variables union the set of terminals.
Okay, first of all, we want terminals, so let me also just put that there. All right, so we also have terminals. And epsilon is always a terminal, so I'll put that as that, right? Okay. Is that all here?
I don't know about union actually. Maybe the
Star, right? So yeah, right? If you write it this way, we're actually completely generalizing. We're saying the rule can map a variable to any string over the variables, right? So over the variables and the terminals, right? So by doing this, we have covered this case, we've covered this case, we've covered this case, right? All of those are allowable rules by defining things this way, and that's great. So you got us started for sure, right? Any issues with this so far? Yeah?
Yeah, I guess like the implication I'm having is that you're trying to establish like a one-to-one relationship where the roles can like have like multiple.
Yeah, so the problem with this is just that as like, I mean, as this example you guys just came up with, right? This actually has 4 different replacement rules for S. Epsilon, 0s1, 1s0, and ss, right? This would only allow there to be 1. So how could we fix that? What do you suggest?
I guess like my approach is like it's a bit naive, but we could try to use like an NFA or like some non-deterministic way of like mapping all the multiverses.
Okay, we want to keep things super simple though, super duper simple. Okay, so definitely you got a token for identifying the problem, but anyone see a suggestion as to how we could get around it? I haven't called on you yet. Yeah. Yes.
Maybe just make it a set of functions.
So just,
So like make R be a finite set of these maps from variable to variable union.
okay. What you are suggesting is that R doesn't have to just be a single function. It could be like any number of functions, right? Okay, that is definitely an option, right? It's a little annoying to write down, right? But I still like where you're going with it. So what you're saying is why use this, like, implicit in what you're saying is like, why use a function at all, right? So let's say we didn't want to do that. And you want to allow R to just be a subset of something, right? So Okay, yeah, one option is what you said. Just think about all the maps. Right? All the maps from V to V union the terminals star, right? This is still a little annoying because it kind of implicitly is saying is that if a particular variable has two replacement rules, then all the variables must have two replacement rules, right? Because like we have two functions, all of which would still have to map, right? So it's just a little annoying to do it that way, right? Does anyone see an option that wouldn't require this to be a function? Like what else could we do here that wouldn't require this to be a function? And I'll just take it open to people and let me ask you again. Yeah.
What we could do is it would be a set of ordered products where it's just like a Cartesian product.
There we go. Right? So just think of it as a table, right? It can have any, you're only allowed to have one variable on the left-hand side of a replacement rule. So that we maintain. But on the right-hand side, you can just have whatever you want. And you can just have anything. Like this is like all the possible, this is some crazy infinite set, right? And of course, we always require everything to be finite. So this has to be finite. A finite subset of like all the possible rules that could ever be, right? Yeah, and that is our definition of a context-free grammar. That works perfectly, right? Questions about it? Yeah.